Hey everybody, this is Reed from Chehalis Skies Aviation, and welcome to the second video in our series called Aviation Knowledge. Today we're going to be talking about airfoil design, what is an airfoil, and some other terms associated with the airfoil. So, without further ado, let's start with what is an airfoil. Alrighty, so what is an airfoil? An airfoil is an object that obtains a reaction upon its surface from the air through which it moves or that moves past a structure. In simpler terms, it's just an object that gains some sort of benefit from air flowing over it. You can see here that what this airfoil looks like is like our little wing. So an airfoil is what our wing is. There's a couple of other examples such as a propeller, or such as the tail portion of an aircraft being the horizontal part and the vertical part, and like I said, also a wing, even the ones on a paper airplane. So that's what an airfoil is. It's something that gains a benefit from air flowing over it. In the case of a wing, the object receives the force of lift as a result from the air flowing over it. The lift we get is that benefit that makes it an airfoil. Now let's talk about some terms and components related to this airfoil. Alright, so the first component of an airfoil we need to talk about are what's called the leading edge and the trailing edge. The leading edge just means the frontmost point on the rounded portion of the airfoil is the leading edge, and the trailing edge is going to be the most aft point of the airfoil where it narrows and tapers at the edge. Between these 2 points, the leading edge and the trailing edge, there's an imaginary line we call the chord line that connects the two. This line is used to reference various components, which we'll talk about here. But one thing to note is this is just an imaginary line. There's no line that physically connects these 2 points on an airfoil. It's just something we use to understand different concepts and use as a reference. So that chord line is just a straight line from the leading edge to the trailing edge, and it is imaginary. One example of the use of the chord line as a reference is going to be to reference something called camber. So camber is the distance between the chord line and the surfaces of an airfoil. It's split into 2 categories, upper camber and lower camber. Upper camber is the distance from the chord line to the upper surface of the airfoil, and lower camber is going to be the distance between the chord line and the lower surface of the airfoil. Another term that's related to camber is called the mean camber line. So the mean camber line is going to be another imaginary line between the leading edge and the trailing edge. However, it's a line that follows a path so that the upper camber and the lower camber all throughout this line are equal. So if you look here, if I take away some of these things here, you can see that the distance between this mean camber line and the upper surface and lower surface are relatively all equal as it goes over the airfoil. And you can see that it's a nice curved line. This demonstrates the curvature of our airfoil. So it's how we assess how curved that makes our airfoil. Typically, when you're hearing about this mean camber line, it's usually referred to just as camber, or the camber of the wing. So if somebody's talking about increasing the camber of the wing or decreasing camber of the wing, they're talking about the camber line and the curvature of the wing, not necessarily exactly the distance between that chord line and the upper and lower surfaces. So that's one thing to note that can be a little bit confusing, but usually when you're referencing camber, it's going to be this mean camber line. The reason we talk about this mean camber line here is because this is something that affects the amount of lift generated by an airfoil. So there's multiple different designs that have become relevant for airfoils depending on the job you want them to do. So some airfoils or wings you want to have the most amount of lift you can generate, because you're trying to get very short takeoff distances or want to be able to fly very, very slow, things like that. But it has a trade-off. For example, with that high lift airfoil, it is going to struggle at high speeds, so it's not going to be capable of flying at very high speed. Let's say you want something on the other end, something super, super fast. At that point, you're going to want an airfoil that generates the least amount of drag and only a little bit of lift. Reason being is all that speed is going to increase that lift tremendously, so you just want something that is going to provide low amounts of drag and a little bit of lift so that you can maintain those super high speeds. So that's where curvature comes in. So the more curved or the more camber, meaning mean camber line, the curvature is going to increase the amount of lift that airfoil can generate. Of course, there's limits to how much curvature. There's points at which it no longer helps. As a general term, the increase of curvature is going to increase lift. One thing to note about this camber is when you're thinking of aircraft and how they design their airfoils and wings, you might say, well, what happens if I want to have a lot of lift and be able to go at slow speeds, but I also want to go fast? So let's say you want to go nice and slow so you can have short landing distances, but when you're up and cruising and you're traveling, you want to be going as fast as you can so you can get to your destination faster. Well, what they use, and you'll see these on airliners and most aircraft, are various forms of flaps. So the flaps on an airplane are on the trailing edge of the airfoil and are responsible for extending, or I should say altering, the camber of the airfoil. So they might come out on the back as a little flap that, instead of going like this, goes down like so, tilts down. It's not a very great drawing. Let's fix that up a little bit. Let's fix that a bit. Tilts down, which allows that camber line to then have a more curved appearance and results in more lift. So that's an example of how they achieve different airfoil designs and changes to get the best of both worlds. So now I want to talk about a couple of different airfoil designs. And I'll throw up here the diagram from the Pilot's Handbook of Aeronautical Knowledge in Chapter 4. And you can see some of the different designs for airfoils. So you can see with the first airfoil here that this airfoil has an appearance of being scooped out, kind of. And it's one of the airfoils that generates the largest amount of lift, but it suffers from very poor high-speed flight characteristics as a result. It's not good at flying fast. The second one you can see is very similar to the first one, but it's modified to make it a little bit more effective at faster flying. It's not as scooped out, but it still has a little bit of scoop. And then the third one you'll see is one that's quite often used on training aircraft in general aviation airplanes. It's got a nice balance of speed, lift, and stability. Underneath that, you can see the laminar flow airfoil here. Now we're getting into airfoils that are designed to provide less drag and are really trying to achieve that higher speed flight, but they start to experience reductions in lift and stability in conditions like high angles of attack, which we will talk about in a little bit. And then finally, in the last two airfoils, these last two airfoils are designed for supersonic flight. These aircraft are going so incredibly fast that they have to design an airfoil that has the least amount of drag and very, very small amounts of lift. Otherwise, too much lift will be generated and it will not be possible for them to reach those speeds. And these last two airfoils you most likely see on military fighter jets and things like that that are designed to go very, very fast. Alright, so that kind of covers our design characteristics and most of the terms associated with the airfoil. We've got two more concepts in terms talking about the airfoil that we'll go over right now. Alrighty, so the last two terms we're going to talk about today are something called relative wind and angle of attack. So, relative wind is a term we use to describe the flow of air as it impacts an airfoil. Relative wind is something that's always going to be parallel and opposite the direction that the airfoil is traveling, otherwise known as the flight path. So the direction of movement or flight path in our example here is going straight forward, as well as this airfoil is following that flight path. As a result, the relative wind is going to be the opposite and parallel to that flight path. So the relative wind, or the air that will be flowing towards the airfoil and over the airfoil, will follow this path here in the orange. One thing to note though is this is not dependent on the way the airfoil is facing. For example, we could have an airfoil pitched up like this. However, if we're still moving in this flight direction path, so the airfoil is still moving in this direction right here, it's going to still have a relative wind of parallel and opposite. And you can see here that that relative wind is actually going to impact a different part of the airfoil compared to the first example. So with the first example, it would impact right here versus right here on our second example. So this is going to change how the airfoil generates lift and a lot of different aerodynamic factors. To describe the difference between these two airfoil angles or impacts that it has on the airfoil is a term called angle of attack. So angle of attack is going to use the components of relative wind and that chord line we talked about earlier. Let me just erase this real quick. So relative wind and chord line. So if we add that chord line, remember the chord line is that imaginary line that goes from the trailing edge to the leading edge. And we're just going to extend it here so you can see this a little bit better. So using these two terms, angle of attack is going to be the angle between that chord line of the airfoil and the relative wind. So you can see here with green, this is our angle of attack. So this green is representing more of that relative wind. I can change that to orange here so it looks a little bit better. So that relative wind is impacting roughly right here on that chord line, and the angle between that chord line and relative wind is what we call angle of attack. So angle of attack is responsible for many flight characteristics, and we'll be talking about this term a lot throughout the series and its role on how the aircraft flies and also its role on being safe. There's limits to how much angle of attack you can have, and depending how you're flying, it's important to always keep in mind how much angle of attack you have while you're flying. But that's going to conclude today's lesson on airfoil design. If you have any questions or comments, please feel free to leave those down below and let me know. If you enjoyed the video and you learned something, leave a like. But thanks for joining me. I hope you learned something, and I'll see you next time.